class, so this section we're going to be discussing ideal gas law. This is 8.7. So when you're given pressure, volume, and temperature of a gas, we can use the ideal gas law equation to determine the amount of gas present. So we can then go on determining the amount, and then we can go on further if we need to figure out the mass of it, meaning molar mass to grams and so forth. This is where we're going to start using chemical reactions with learning about the ideal gas law. So the ideal gas law is a combination of four properties used in the measurements. Ones by now you should already be familiar with: pressure, volume, temperature, and gas. But the ideal gas law is listed here. There's one more. R is a gas constant. I'll cover that in a little bit. So when we rearranged the gas law equation and so we solve for R. So if we plug in the STP conditions, meaning 273 Kelvin, 1 mole of gas, 22.4 liters as a volume, and so we see the 1 atm as a pressure, 22.4 liters, 1 mole, 273. By the way, when we do our ideal gas law, it's always Kelvin, never Celsius. And what it does is it gives us a gas constant. And you see there should be a dot here and there should be a dot here, but I couldn't find a dot with some of these things. But this is the gas constant that is a part of this. So this is the gas constant I use. There's a slides that are given to me for this book that there's another gas constant. I'm going to show it to you, but I'm going to be honest. This is the only gas constant I know. I will explain why I only use one gas constant and not the 5 or 6 that are out there, because one, it's ridiculous. We don't need to learn all of those. All you need is one. Okay, so this is the gas constant. Now, I will tell you that sometimes this figure here is 4 sig figs and sometimes it's 3. Your book is showing 3. I know it as 0.08216. So there is more. It's not exact, and you need to be aware of that. Okay, because it can change to 4, it can change to 3. So real gases show deviations in behavior. They do not follow the rules or laws that we would really like to. But we can use this equation to get this approximate a closest value to what's actually happening under typical conditions. So here is the next gas constant. And what is the difference here? Well, the difference is the pressure. All the different gas constants will have different amounts because the pressure will be different. You can use different units, which will change everything else out here. This will be the same, this will be the same, this will be the same. It's millimeters mercury, which will change everything. I don't know this gas constant. I would have to look it up. I change everything. So if you're given a problem, we're going to go through a couple problems. We're going to go through a problem. If you're given a problem and the pressure is not in ATM, all I do is convert that pressure to ATM, use this gas constant, and then if the answer has to be converted to millimeters mercury, I will convert it back to millimeters mercury. That's how I avoid having to learn 6 different constants. I've never done it. I just convert, use it, and then convert back if I have to. It's not a big deal. You can see. I will show you as this goes on. So that's what I'm pretty much saying here, is that I convert what I need to, and then I convert it back. So for instance, if you're given a problem that you have milliliters, convert it to liters, plug it into the ideal gas law, and then if you have to plug it and then you have to convert it back to milliliters, convert it back to milliliters for the answer. That way you keep it with one gas constant and you don't have to change everything. You don't have to learn for everything. You just do one. So let's do a problem. Dinitrogen oxide, which is used in dentistry and is an anesthetic, also called laughing gas. What is the pressure in ATMs if you're given 0.350 moles at 22 degrees Celsius in 5.0 liter container? So for instance, this would be a perfect one. Let's say that this answer, this variable for volume was in milliliters. I would instantly convert it to liters to use it in the ideal gas law. Because you need to use the gas constant that matches, and you don't mess with the gas constant. You have to do other things to make it fit, but it's never changing the gas constant. You can use other gas constants, but you can't really, I would never suggest toying with that gas constant in the conditions that are there. So what is given? So we're given a volume, the moles. Always change the temperature. Never use Celsius. When we deal with gases, we do not use Celsius. We use Kelvin. And then the ideal gas law and the gas constant that I use, that 99% use. Okay, so we need to rearrange the gas law equation to solve for pressure. This is how it's normally given to you, and you just rearrange to whatever you need. Do you need moles? Then you'll bring this over. You need volume? Then you bring this one over. This is how it's usually left so that you can change it very easily into what you need to rearrange it to. So let's take a look at what we have. We have our moles, which is here. Let's take a look at the back one. I should have copied this one over and I didn't. But this is what we're looking at. We have P equals nRT over volume. I apologize. I like to always show what the equation is before, and I missed that on this one. But here's our moles, gas constant, temperature over volume. And let's make sure that's that. N, gas constant, temperature over volume. Yes, it is. Now, if you do this correctly, everything, all the units will cancel out except for the variable that's missing. So the moles will cancel with the moles. The gas constant's here. Temperature will cancel with temperature. And then the liters will cancel the liters, and leaving you with the ATM, which is what we have here. So this is a problem that I'm talking about, that you might have to tweak things before you plug it in. But once you plug it in, you should be fine. And if you have to convert to something after, it's not that big of a deal. You get used to doing these and you'll understand a little better. Like, oh, I can actually have freedom to do some of this stuff. So we answered this problem. It's 1.7 ATM if we're given the variables. And so you're given pretty much 3 variables, a gas constant, and you'll have to solve for the last gas variable. So here is the 2 gas constants. I use this one only. I don't touch this one. I don't even know this one. Only 1 ATM, the volume, what we showed. Basically, everything that we showed on the other slide equals this amount. This is what I know. And this is the only one I know. Sometimes I use 4 sig figs though. Okay, so gas law and chemical equations. Now we're going to move into something that seems like it's going to be more difficult, but honestly, you've been doing this whole time if you're getting to this section. It's not really a bigger deal. You're just doing a few extra steps. So gases are involved as reactants and products in many chemical reactions. Typically, the information given for a gas and reaction is its pressure, volume, and temperature. We can use the ideal gas law to determine the moles of a gas if we are given the number of moles for one of the gases in the reaction, the moles of any other substance using a molar factor. What this means is that we're usually given pressure, volume, temperature, but we're never given the moles. Not most of the time we're not. You have to actually do extra steps, which I'm going to show you in a problem. You'll have to figure out the moles in order to get at something. So you're usually going to be given a reaction. Sometimes you might have to balance the reaction first, and then you will have to determine the moles of a reaction and then do stoichiometry, dimensional analysis in that reaction to get to the product that you want. So let's say we have a reactant and we want to know the product. So this is, you'll determine the moles of the reactant, and then do stoichiometry through ratios of how many coefficients to get to the moles of the product. And then you can plug all this into the ideal gas law, which is what we're going to do. So if what I'm saying doesn't make sense, this next problem is going to cover exactly what I'm talking about. So, nitrogen gas reacts with hydrogen gas to produce ammonia gas. How many liters of ammonia can be produced at 0.93 ATM, 24 degrees Celsius, from 16 grams sample of nitrogen gas and excess hydrogen gas? So, they're telling you a few things here. This is not a difficult problem. It's just something new. But you've been doing all of this separately in other steps. We're now just going to combine everything. So here is, it's telling you that we're interested in the sample of nitrogen gas and an excessive gas. So this is a limiting reactant. We're not worried about excess. That's all this is pointing out. We're not really involving hydrogen. It's an excess here. We're interested in nitrogen to ammonia. So the nitrogen gas reacts with hydrogen to produce ammonia. How many liters of ammonia? We're interested here in how many volumes what's the volume in our answer from all these steps is we are interested in the volume of this ammonia gas, and it's got to be in liters. But before we can do that, we're going to have to work on this chemical reaction because we don't have any information about ammonia. We only have information about nitrogen. And then we're given pressure, temperature that must be converted, and we're given the mass of nitrogen gas that we get to use. So what I was saying here is that we take the mass, we use molar mass to get to moles, and then we can do a ratio to determine the moles of this, and then we can plug it in to the ideal gas law. And that's what we're going to do. So this has got to be 2 steps. One, we have to focus on the reaction first and get to moles of ammonia, which we're not there yet. So we're going to use the mass amount to get to nitrogen first. So let's plug this in. What are our steps? We have our grams of nitrogen. We're going to use the molar mass of grams per mole. We're going to get to the moles of nitrogen. The mole to mole factor here is a 1 to 2 factor. So there's 1 mole of nitrogen for 2 moles of ammonia. That will get us to moles of ammonia. Then we're going to use ideal gas law based on the moles, and that's going to determine our volume, because now we'll have moles, we'll have temperature, we'll have pressure, and we will need to solve for volume. So here are our conversions. So we have 1 mole of nitrogen with the molar mass, and we can set that up. We have 2 moles to 1 mole, and we can set that up. So this is everything I discussed on the other page. So let's set it up. We have 16 grams, and we use our molar mass to get to our moles, which we do. Now we can use the ratio between 1 to 2, and we solve for that. So nitrogen is now gone. We are in ammonia, which is what we want, and we have 2 moles of ammonia. So when we plug all this in, we have 1.14 moles of ammonia. So what do we have? We have our pressure, we have our moles of ammonia, we have our temperature, and we're missing the volume. So now we can plug in our pressure, our moles, gas constant, and temperature. We can isolate volume and solve for that. So we need to focus on this reaction first before we could have even gone further. So now we're going to plug this in because we isolate for volume, and we have our moles, our gas constant, our temperature, and then our pressure. So again, if we did this right, everything should cancel out except for the volume. So we have moles that cancel, we have our temperature that cancels, and we have our pressure, which leaves liters. So our answer in this problem is 29.9 liters of ammonia. So everything cancels out. That's a good indication that we have at least set this up right. Okay, so this problem seems difficult at the beginning. You just have to understand that you have to maybe do additional steps before you do the ideal gas law, but these are steps that you've been doing separately, and now we're just going to combine them. Pull everything out, take your time to figure out the stepping stones you need to get to the next unit, whatever it is, moles of this, or get out of grams. So the volume here, the mass was grams, so we instantly know we got to get that to moles. That's why I say write down all the units, because sometimes knowing just the units, if you're stuck, will get you to the next step. Okay, and that's it. Thank you.